Chapter 3, Rocks, Materials of the Solid Earth. Okay, density. Got a few definitions here for you. Mass is the amount of matter in an object. Weight is the effective gravity on a mass. And volume is how much space an object occupies. So using those, we can figure out density, which is mass, the amount of matter in an object, divided by its volume. Okay. Specific gravity is its density divided by density of water, to compare how dense an object is versus the density of water. Okay. At this point, if you want, you can pause and go into Blackboard and watch the 7 layers of density experiment YouTube video, or the float or sink YouTube video that gives you examples of differences in density. Okay, to the rock cycle. The rock cycle shows the interrelationships among 3 rock types. Earth as a system, rock cycle is a major system, and a brief description of the system is molten rock or magma slowly cools and crystallizes, forming igneous rock. Igneous rock then gets weathered, transported, and deposited. Then those sediments that get deposited get lithified, or lithification turns those sediments into a rock again, and this rock is sedimentary rock. Then this rock, under heavy pressure and temperature, could be changed or metamorphosed into metamorphic rock, which later could be buried and melted, and we have magma again. So that's the outer loop of our rock cycle. But the cycle doesn't always take place going around that whole circle. It takes shortcuts to cross the circle. Okay, and in this diagram, we'll see that igneous rock, well, it may get weathered and turn to sedimentary rock, and get metamorphosed and become metamorphic rock, and then may melt and become lava again. Well, actually, igneous or sedimentary or metamorphic rock can be metamorphosed. Metamorphic rock and sedimentary rock and igneous rock get weathered to become new sedimentary rock. So shortcuts can be taken in the rock cycle. Igneous rocks form as magma cools and crystallizes. Rocks formed inside the earth are called plutonic or intrusive rocks. Igneous rocks formed on the surface of the earth are formed from lava, so it's magma but has come on out to the surface of the earth and no longer has gas in it, and those are called volcanic or extrusive rocks. Okay, magma, as it crystallizes, ions are arranged into orderly patterns. Crystal size is determined by the rate of cooling, how fast that magma cools. Slow rate forms large crystals. A fast rate forms microscopic crystals. A very fast rate forms glass. Classification of igneous rocks is based on the rock texture and mineral constituents. So we decide which igneous rock is which igneous rock, and we name them based on certain classifications, and the most important one is texture. Texture is the size and arrangement of crystals. The types are fine-grained from fast rate of cooling, coarse-grained or larger crystals from slow rate of cooling. Porphyritic has fine-grained crystals and coarse-grained crystals because there are 2 rates of cooling during the making of that rock. And then glassy, very fast rate of cooling. Okay. This is a very fine-grained igneous texture. You can tell it doesn't look like glass or anything, but you also can't really identify the individual crystals because they're so small. Coarse-grained, you can pick out which crystals might look like plagioclase or feldspar here, or the clear gray crystals are going to be your quartz, and the black crystals are going to be your biotite. So you can actually identify the minerals in that rock. It's so coarse-grained. So porphyritic igneous texture. These crystals, probably plagioclase, probably formed first while the rock was cooling really slow, and then that magma moved to an area where it's going to cool faster, and the rest of the magma formed a very fine-grained matrix around those crystals. So you have both coarse-grained and fine-grained texture equaling porphyritic. A glassy texture, like obsidian, is volcanic glass. That magma cooled so fast that basically froze and formed glass. So we also, besides the texture of the rock, we also want to talk about the mineral composition in order to identify our igneous rocks. Bowen's reaction series shows the order of mineral crystallization, and this is influenced by the crystal settling in the magma. Okay. So first, a classification here. We have our classification by texture. These are our coarse-grained igneous rocks, our fine-grained igneous rocks, our porphyritic, and our glassy igneous rocks. We also classify based on color or percent of dark minerals. Here it's mostly our felsic or light silicates. Here we have more of our mafic or dark silicates. Okay. So our granites are very felsic rock, our granitic rock. It's going to be mostly quartz, potassium feldspar, sodium-rich plagioclase feldspar. And coarse-grained granitic or felsic rock is granite. Our fine grain is going to be rhyolite. Okay. Our andesitic or intermediate, so in between felsic and mafic, or in between light and dark, is our andesitic. So we're going to have a lot of amphiboles and sodium and calcium-rich plagioclase feldspar. These are going to be our diorites and our andesites for our coarse grain and our fine grain. Our basaltic or mafic rocks are pyroxene and calcium-rich plagioclase feldspar. So they form our gabbro, which is our coarse grain, and our basalt, which is our fine grain. Then on the extreme, we have our ultramafic, full of olivine and pyroxene, very few felsic minerals. And our peridotite and comatite are going to be our examples there. Just again with that Bowen's reaction series, as the magma cools, the lower temperatures, crystals start to form. So the high temperature, at high temperatures, everything stays molten, and as it cools, our quartzes are going to form, our micas are going to form, potassium feldspars, until eventually we have all of our minerals forming into crystals. Okay, so naming our igneous rocks. So our granitic rocks are mostly the light-colored silicas, quartz and feldspar. We refer to them as felsic, which is just putting together the words feldspar, fel, and the sil in silica for the quartz. So felsic, high silica content, about 70%. Common rock we know of is granite. Here's a picture of granite again. Now basaltic rocks contain much more dark silicate minerals and calcium-rich plagioclase feldspar, so we call them mafic because they have a lot of magnesium in them and ferrum or iron in them. And a common rock is basalt. Here's a nice chunk of basalt here. Other compositional groups are andesitic or intermediate and are ultramafic. So andesitic is between felsic and mafic, and ultramafic is more mafic than our mafic. Okay, next group, major groups of rocks, is our sedimentary rocks. These form from sediment or weathered products or broken down other bits of rock. About 75% of all rock outcrops on continents are sedimentary rocks, used to reconstruct much of Earth's history because they contain clues to past environments. They provide information about sediment transport, and they may also contain fossils. Economic importance of sedimentary rocks: they provide us coal, petroleum and natural gas, and sources of iron and aluminum. We classify them partially based on size of particles. Our detroidal rocks are made of material and solid particles, and we classify by particle size. Our common rocks here are shale, sandstone, and conglomerate. So over on the left side of our sedimentary rocks is our detroidal sedimentary rocks that we identify by grain size. Our other kind of sedimentary rocks will be our chemical and organic sedimentary rocks, and they form crystals that come out of solution and precipitate. So these detroidal ones, the coarse grain ones, have grains that are over 2 millimeters in diameter. That sounds small, but that size and up, geologists consider gravel, and those will be our conglomerates and our breccia. The difference between conglomerate and breccia is that conglomerate, the grains have been rounded by longer transport. These grains turn into rock, into sedimentary rock, farther away from the parent rock than these grains, which are still very angular. They haven't been worn down, but being washed down a long stream or a river. Now our medium grains are 1/16 to 2 millimeters in diameter, and these are sand-sized grains. Okay, now this will be a sandstone. Unless it's made of a lot of feldspar, then it'll be kind of reddish, and we'll call it arkose. Okay. Now the fine grains are smaller than sand, and these form your mud siltstones, if there's some quartz in there still, and shales or mudstones. Here's a picture of shale with plant fossils. Here's our sandstone. Here's a conglomerate. Okay, now the other major group of sedimentary rocks are the chemical rocks. These are derived from material that is once in solution and precipitates to form a sediment. They directly precipitate as a result of physical process or through life process, biochemical origin. Okay. Common sedimentary chemical rocks are limestone, which is the most abundant chemical rock, microcrystalline quartz, which is precipitated out quartz known as chert, flint, jasper, or agate, and then our evaporites, this is rock salt or gypsum, and then we also have coal. Okay, loose sediments. Okay, now how these sedimentary rocks form typically are through lithification. So loose sediments are transformed into solid rock. Lithification process includes compaction. The sediments get pushed together, compacted together, moving airspace. And then cementation, as fluid passes through, calcite and silica or iron oxide will precipitate out and form a cement that glues those particles together, forming a rock. Now, sedimentary rocks, the material becomes sedimentary rock, gets laid down in layers, and to actually see layers or beds, or we also call strata. Bedding planes are planes you can see separating the strata, like a break. And then there's fossils. Many sedimentary rocks have traces or remains of prehistoric life. They are the most important inclusions. They help determine past environments, help us determine how old the rock is, and are used for matching rocks from different places. Now the next group of rocks is the metamorphic rocks. These are the changed form rocks produced from pre-existing igneous rocks and from sedimentary rocks or other metamorphic rocks. So metamorphism, the process that makes metamorphic rocks, takes place where pre-existing rock is subjected to temperatures and pressures unlike those in which it was formed. Okay, degrees of metamorphism, okay, is one way we classify them, exhibited by rock texture mineralogy, very low-grade metamorphism. So when a rock is lightly metamorphosed, it may still show some traces of what it looked like before. So like when shale becomes a slate, you'll still see shale was laid out in layers, and when it comes to slate, you'll still find the bedding planes. Those are planes the slate will want to break apart to make tiles. Then, in contrast, we have high-grade metamorphism, which wipes out any of the features, original features of the parent rock. Metamorphic settings. Metamorphism happens in two kinds of settings. Contact or thermal metamorphism occurs near a body of magma. So deep under the earth, we have a body of magma. That magma is really hot, so the rock next to it's going to get really hot. And that rock that's not melting but gets really hot, well, that's going to metamorphose. So those are going to be smaller areas of metamorphic rock. Now, regional metamorphism happens due to directed pressures and high temperatures during mountain building. So this produces the greatest volume of metamorphic rock. Okay, so the agents of metamorphism, what causes metamorphism, are heat, pressure or stress. The pressure or stress can be from burial, called confining pressure, and differential stress, so different amounts of stress from different directions, that occurs during mountain building. Also, chemically active fluids, so mainly water and other volatiles, they'll promote recrystallization by enhancing ion migration. Okay, so talking about pressure and metamorphism, as sediments are laid out, they get deeper and deeper. And they'll actually, from all the sediments around them, they're going to have equal pressure, confining pressure. And so as this big chunk of sediments, when it's down below here under so much other layers, it gets compacted to a smaller shape because all the airspace is being pushed out. Now, if it's held under if it metamorphoses under differential stresses, those beds will no longer remain as they were, they'll be deformed, and you'll end up with these wavy banded layers. Okay, texture that we'll find in metamorphic rocks, foliate texture. The minerals are in parallel alignment. They actually form streaks. So the dark minerals will line up, the light minerals will line up, and these minerals they're going to be lining up perpendicular to the compressional force. Non-foliate texture contain equidimensional crystals resemble a coarse-grained igneous rock because the grains in that rock, let's say the grains in a sandstone, that quartz recrystallized and started to interlock again. So that quartz, so it's sandstone, starts looking kind of like a one mineral igneous rock. Okay, so here the directional forces of foliation. So here we have our igneous rock with the grains pointing in any which direction they want. Then under metamorphism, when you apply pressure from more pressure from side to side, and maybe a little less from the top to bottom, those grains are going to start lining up and try and point in the same direction. So you end up with lineations of dark bands and light bands of the minerals. Common metamorphic rocks, the foliated ones will have slate, which is fine-grained and splits easy. Schist is strongly foliated and platy, as a mica grains will, the biotite muscovite, they will get bigger and they'll be very shiny. Types of, and we name them based on the composition. So if there's a lot of mica, we'll call it a mica schist. Okay, so here's our chart here. So in increasing amount of metamorphism, our slate is the lightest, then we get schist, and gneiss is like an igneous rock. It's like a granite, except all the grains are all lined up. Okay, so we have this foliate texture. The grains are lining up. The slate is formed of shale or mudstone or siltstone. The schist will be a shale, mudstone, or siltstone. The gneiss could be from shale, granitic, or volcanic rocks. Okay. Now those are foliated. So the non-foliated, we have marbles, quartzites, and anthracites. The marbles, okay, the limestone and dolostone, their calcite grains or dolomite grains will recrystallize and form these interlocking crystals. Quartzite is from quartz sandstone. So the quartz grains will recrystallize and fuse together. We have a very hard rock called quartzite. The marble probably would not scratch glass, but the quartzite probably would. I'm thinking if we're trying to test and decide which one's which. Anthracite is actually a metamorphosed coal, so bituminous coal. And there are more and more compression. More of the moisture gets pushed out of the coal, and it turns very hard and can exhibit conchoidal fracture. This is the most has the most energy per unit area of the different coals, but it's harder to mine. This forms in mountain building events. So the layers are deformed and hard to pull out. Okay, so some more about these metamorphic rocks. A very common one is gneiss. Okay, so it's the strongest segregation of stenocate minerals. It's a very banded texture. Now the non-foliated, the most common is the marble, which is formed from limestone, large interlocking calcite crystals. So here's a picture of our gneiss. Nice bands of dark minerals versus light minerals. We also have quartzite. Its parent rock is quartz sandstone. The quartz grains are fused together. Here's a picture of marble. Sometimes we have this nice veiny patterns that form nice pretty patterns when we cut and polish marble to put on our kitchen floors or kitchen counters. Okay, now also it's important about rocks and minerals is that we get our resources from them, metallic mineral resources such as gold, silver, copper, mercury, and lead. Now these minerals may be grouped together or concentrated by igneous processes and metamorphic processes. Okay, so most important ore deposits are generated from hydrothermal or hot water solutions. They're hot, they contain metal-rich fluids associated with cooling magma bodies. And these types of deposits will include vein deposits and along fractures or bedding planes where the hot liquid seeps in, and disseminated deposits where the liquid seeps throughout the rock. Okay. Non-metallic mineral resources make use of the mineral's non-metallic elements, physical or chemical properties. So these two broad groups are are building mineral resources such as limestone and gypsum, and the industrial minerals of fluorite, corundum, and sylvite. Okay. There's a picture of a non-mineral resource being mined. I think they're mining marble here.